All right, just one sort of important announcement to give. I doubt if it'll affect any of you, but in case it does. Normally on Tuesdays and Thursdays, I have office hours from 10:45 until 4:30, okay? Most Tuesdays and Thursdays, that's what's on my locator card. However, tomorrow morning at 9, I have an appointment with my hematologist down at the Kirkland Clinic in Southside Birmingham. So I won't be coming to campus tomorrow morning, because if I came to campus, I'd have to turn around and leave in 15 minutes before my class ever started to get there in time for my appointment. So I'll just be going straight to my appointment on tomorrow morning. That means I'm going to miss my first class tomorrow, okay? But I met with them Thursday and we went over it, and they agreed to meet at 11 o'clock on tomorrow rather than 8:30, because I won't be here at 8:30. So that means my office hours won't be starting at 10:45. They'll be starting at 1:15, okay? So tomorrow my office hours, rather than being 10:45 to 4:30, will be 1:15 to 4:30. And actually that also means there's less opportunity. I didn't think about that before, for me to get in touch with the people at Cengage, but I'll try to get that done if possible tomorrow. Okay. But we'll have to see. Okay, here is the mirror, right? All right, good deal. But now we've got enough for a volleyball game. Okay. Okay. Any questions on anything we've done so far? I did mean to say this. Forgot to make any marks in my book, but they came out with a memorandum last week, and I thought I had it in my book, but I don't see it now. It's from the Vice President. It's that time of year, time of the term, which is never known when it's going to happen, but it always happens, when he says, don't let unpaid students come to class anymore. Okay, so if you have not completed your payment process, wherever that may be, please get that done as soon as possible, because at some point, maybe even this week, they're going to remove unpaid students from the roll. Now, usually they let you back in once you do your payment, but it's sort of a big administrative hassle that you have to contact offices and get approvals and all that kind of stuff. So please, if you know some of your classmates that haven't completed payment, please get that done so you don't have that interrupted. He said on the memorandum that we are not supposed to let unpaid students come to class after we make this announcement. Frankly, I'd rather you be here than not be here. But here's how I look at it. If you're not paid, you're not on the official roll. If you're not on the official roll, there is no way I can give you a grade. So if you want to sit in here all term without paying, and then at the end of the term not get a grade, that's free world. I mean, free country. You can do it if you like, but I cannot give you a grade if you're not on the roll. So you're welcome to sit here as much as you like. I'd rather you be here, if you are going to complete payment, than miss classes and then have to catch up. So anyway, that's not official policy. That's how I like to do things. So point is, try to get your payment completed as soon as possible. If you haven't. I think all of you have, but that's not one of the big things I go around monitoring. So hopefully y'all are all in good shape. Okay. Any questions on anything before we get started? All right. We're in Chapter 3, which is Applications of Differentiation, and 3.2 is Rolle's Theorem, and then later we'll get to the mean value theorem. Now, I don't know if you remember what Rolle's Theorem was. A couple of you weren't here, so let's go back a couple slides. And here is Rolle's Theorem. If f is a continuous function on some closed interval a to b, okay, and it's differentiable on the open interval a to b, then, and another one, if f of a at one endpoint is equal to f of b at the other endpoint, meaning they're the same value in there. So it's a continuous function, differentiable function on that open interval a to b, and f of a is equal to f of b. Then there's at least one number c in a to b, somewhere down here between a and b, such that f prime of c is equal to 0. No way around it. If it starts here and winds up there, there's got to be some point in there where there's either a relative minimum, maximum, a relative minimum, or it's constantly that same value. And then at every point, the first derivative is 0. Okay? Now, there may be tons of points where its first derivative is equal to 0. There may be many c's in there, but there's got to be at least one. Okay? So that's Rolle's theorem. So what we're going to be doing now is, on example 2, we're going to do this. Let f of x equal to x to the fourth minus 2x squared. Okay. Says find all the values of c on the interval. Find all c's. All right, say c's and write a's. Okay, I think I was writing all, but I guess I could go on and write all, so I will. Okay. Find all c's such that, double dot sort of looks like a colon, is such that, before I get there, all c's that are elements of -2 to -2, -2 to +2, okay, such that f prime of c is equal to 0. Okay? Now, can anyone tell me, without even plugging them in, whether this meets the conditions of Rolle's theorem? Second? No. Okay? Yes, you can. You just don't realize you can. Number one, it's a continuous function. All polynomial functions are continuous functions. So we know that's true. Okay? It's differentiable on the open interval. Yes, all polynomial functions are differentiable on any interval. Okay? So you know that. Now, here's the part you may not realize that you know. Okay? Is f of a, which is -2, equal to f of b, which is +2, without plugging in? You do know that, because what kind of function is this? What do you notice about those two exponents? Give me a just observation. Tell me something in common between those two exponents. Second, they're both even. Okay, perfect. Okay, Reginald's here. That's even better. Okay. All right. And if all the exponents in a polynomial function is even, what kind of function is it then? Give it a shot. If all the exponents are even, what kind of function is it? Same word. Even! Now, what does it mean to be an even function? You know, remember the rule for that? That f of a is the same as f of minus a. That's what it means to be an even function. Okay. And with that, even, Jalen came back. Yes. Okay. Now do you see f of -2 has to equal f of +2 because this is an even function. So you did know that without plugging in, whether you realize it or not. But let's plug in and just check. If you plug in a -2 here, -2 to the 4th power is 16. minus 2 times negative 2 squared is negative 2 squared. 4, yeah, and then 2 times 4 is 8. Okay, I got it. You're already jumping ahead. 16 minus 8 is 8. Very good. Let's plug in a positive 2. Positive 2 to the 4th is 16. Positive 2 squared is 4. 2 times 4 is 8. 16 minus 8, again, is 8. So yes, they are true. All the conditions of Rolle's theorem are met. Okay? So we know there's at least one C somewhere in between minus 2 and 2 where the first derivative is equal to 0. It says find them all, indicating there may be more than one. So guess what we're going to have to do? Take a derivative. Perfect. So f prime of x is equal to what? 4x cubed. Next, minus 4x. And what can we do with that? Oh, we want to know where it's equal to 0, so we set it equal to 0. And what can we do with that? Okay. I don't know if I've told y'all before my question, and if any of you find it offensive, I won't do it. But when I asked a question in any math class, what's the F word? Guess what it is? And get the mind out of the gutter, okay? Anyone want to make a guess? Factor, of course. So in math class, the F word is factor, okay? Anyone offended by that? I won't say it if you are, okay. So what's the F word? Factor. Can this be factored? 4x times x at x squared minus 1. Excellent. Equals 0. Well, guess what we're going to do next? What's the F word? Keep factoring until it's totally factored. Can we factor this 4x? We can't. I mean, you could do 2 times 2 times x, but we're not going to mess with that. It's a monomial. But what can we do here? Is that factorable? Say again? X plus 1 times x minus 1. Perfect. Okay? Now we've got it fully factored. What do we do at this point? Got any entities multiplied together that equal 0, what does that tell you? If you have any number of factors multiplied together equals 0, what does that tell you? Only way you can get 0 as a product is if 0 is one of the factors. Can you come up with any two numbers? You multiply together, get 0, and one of them not be 0. Do it. If you can find that, you win the Fields Medal. It's the highest honor given in mathematics, okay? It can happen, okay? One of these has got to be 0. So guess what we're going to do? If you have a string of factors equal to 0, what does that tell you? Either, y'all know how to do this, either good morning, Vietnam. Okay, are y'all here? Okay, we're at the class. Come in, please. Either 4x is equal to 0, or x plus 1 is equal to 0, or x minus 1 is equal to 0. One of those has got to be equal to 0. It may be all three, or two of them, or whatever. At least one of them's got to be 0. Otherwise, you cannot multiply three numbers together, get 0 as a product, unless one of them is equal to 0. Okay? Now, what does that first one tell you about x? Anybody? What does x have to be? 0. So either x equals 0, or what does the next one tell you? X equal -1, or x equal 1. Hey, guess what we just done? We found all 3 c's for this function for which the first derivative could be 0. Either x is 0, so plug it in here and see. Here's your f prime. Plug in a 0, you get 0 minus 0 is 0. Plug in a -1, and you get -4 plus 4 is 0. And then because this is an even function, you know that's got to work too, and it does. 4 minus 4 is equal to 0. I'm sorry. Yeah, that's an even function. This is an odd function. That has, if you plug in f of minus x will be minus f of x, and that's going to be 0 as well. So all 3 of those. Those are our 3 c's that on that interval for which the first derivative is 0. So x equal, oh, there it is right down here. Those are your 3 c's. Okay. Any questions about that? Does everybody see that? Does it make sense? All right, good deal. All right, that was example 2, and in the book they got x equals 0, 1, or -1. Excellent. Now, they have little blurbs like this periodically. A technology pitfall. A graphing utility can be used to indicate whether the points of a graph in examples 1 and 2 are relative minima or maxima of functions. When using a graphing utility, however, you should keep in mind it can give misleading pictures of graphs. For instance, they show one here, which is truly a very weird function. F of x equal 1 minus x minus 1 squared minus 1 over 1,000 times x minus 1 to the 1/7 power, or the 7th root of x minus 1, plus 1. With most viewing windows, it appears that it has a maximum at 1, okay, when x equal 1. But if you expand your viewing window, and the reason for that is look at that coefficient of 1,000. That's going to really blow things up number-wise. You have to expand that. It says you need to graph analytically, not just using your technology. I don't know why they put them in, I guess because people depend on that too much. But anyway, we're ready now for the mean value theorem. It's a mean value theorem at that, you know, so I think this is still example 1. There we go. All right. Now, this follows from Rolle's theorem. Rolle's theorem can be used to prove another theorem called the mean value theorem. What that means is f is continuous on the closed interval a to b, just like in Rolle's theorem. Differentiable on the open interval a to b, just like in Rolle's theorem. Then there exists a number c in a to b such that, okay, f of c, the f prime of c, the first derivative of the function at some value c is exactly equal to the slope between those 2 points. A f of a and b f of b, okay? That's y2 minus y1 over x2 minus x1. There is some value c whose derivative is exactly equal to the slope between those 2 points, the endpoints. Okay? And that kind of makes sense too. Okay? They don't do much more with it. In the book, they spend most of a page proving it. Okay? And I wish they showed that. It's a pretty good illustration. Okay? I'll try to just draw it simply. Wait, I'm sorry. Okay. let's just say we have a function here, okay? I'm not going to draw the same one that's in the book. Something like that. Here's f of a, and let's make b, let me change that ever so slightly. Okay, all right, let me try that again. Okay, so here's a, f of a, and here's b, and there's f of b. Okay? Now, what the mean value theorem says, if you draw the line between that, okay, the slope of this line, m of a to b, I'm just going to say it that way, the slope between x equal a and x equal b. It says, okay, now the requirement is f be continuous. You can't have any gaps, missing values, or anything like that. And differentiable. That means, and here's another way to say this, smooth and continuous. To be differentiable, it's got to be smooth. It can't have any cusp or corners or things like that. It has to be smooth and continuous. So it's continuous and differentiable on the open interval a to b. Okay? Then there exists some number c in a to b such that, now you can have a lot more complicated looking function than that. That's fine. This is a fairly simple one. Okay? A number in between here whose slope is the same as that. Well, it's pretty obvious that there's some point up here. The tangent line to this is exact. Whoa, I didn't quite get it, did I? Here, maybe. Yeah, maybe even here. Yeah, that looks pretty good. Here to here. So in other words, there is some tangent line, there is some point on this curve in between A and B such that L prime is equal to the slope of that line. That's called the mean value theorem. Now, you might say, where does mean value come from? Don't worry about that, okay? It just means there's some point in between A and B that has the same slope there. Now, if this function went up and down several times, there may be several of those slopes that are equal. This one has one and basically only one, okay? I tried to do a couple that weren't that, but yeah. So their drawing's a little bit better. There also, on the same page, is a little blurb on Joseph Louis Lagrange. An interesting lifetime here. His lifespan, he was French, by the way. 1736 to 1813. If you think about that, what was happening in this country between those years, 1736 and 1813? 1736, we were still colonial. In fact, I think, I'm not even sure, Georgia, I think they may have been 32. So yeah, all 13 colonies probably were in existence when he was born, okay, if not shortly thereafter. And during his lifetime, which unfortunately wasn't, let's see, that's 64, 77, a pretty good lifetime span for that time of thing. During that time, the American Revolution happened, 1776, and guess what? Who helped us more than anybody in the American Revolution? Who was always fighting the English anyway? The French, exactly. The French were great helps to us. And he would have been just about the age that he probably politically, I don't know which way he was politically, probably was more than likely supporting the American cause. I don't know that he fought, but that's okay. Oh, and by the way, he was born in Italy. Okay, I said he was French. I didn't realize that. It's such a French-sounding name, and Joseph Louis Lagrange sounds, but he was born in Italy. They didn't have much to do with us then. He held a position in the court of Frederick the Great in Berlin, who was the Holy Roman Emperor at the time, though he as my high school English teacher said, the Holy Roman Empire was neither holy, nor was it Roman, nor was it an empire. So she went into that. But anyway, he actually looks very Italian now that I think about it. But anyway, so forget what I was saying there. But so evidently he was Italian, but he did hold a position there. Great mathematician, though, by the way. So I guess he's the one. It was first proved. Mean value theorem first proved by Lagrange. Okay. Potential paper topic is what I was getting at there. Hint. Because in this, of course, my best class ever, and we're getting close to halfway through the term, one paper turned in so far. One? Just one? Please, folks, keep them going. Okay. So anyway, here's mean value theorem. First proved by Lagrange. Okay. So example 3, top of page 177, says here's a function for f of x is equal to 5 minus 4 over x. Find all the values of c in the open interval from 1 to 4 such that f prime of c is equal to the slope between those 2 points. Now, when I see a function like this, hopefully for you too, you'll hear a few sort of in the background bells, whistles, sirens going off saying warning. What's something you need to pay attention about that function right there? Second? X cannot equal 0 because 4 over x would be undefined. So if this interval they were talking about here included 0 in it, all bets are off. I mean, you may find something, but it's not guaranteed because remember it has to be a continuous function. And this is not continuous at x equals 0. But guess what? 1 to 4, that's outside of that. 0 is not included there. So that's all that's required. It has to be continuous and differentiable. You can differentiate that between 1 and 4. So let's do it. Okay? What would you do first? I think I know what you're probably going to say, but I will make one suggestion before you do it. What would you say? What you going to do first? Anybody? Second? Okay. At some point, we're going to do that. Okay. If you're doing this part of it, yeah, let's go on and do that then. Okay, let's go on and plug in a 4 first then. Okay? If you plug in 4, what do you get? 5 minus 1 is 4. Okay? Minus, plug in 1, and what do you get? So I got 1 over 4 minus 1. That's 3 over 3. That's equal to 1. Okay? So that says that the slope between those 2 points is 1. There's got to be some value c in between 1, 1 and 4, 4. Okay? Happens to be on that. That's bizarre, isn't it? Did we do that right? Yeah, I guess we did. Okay? Such that, yeah, that's right. Such that f prime of c is equal to 1. Okay? We've figured out what the slope is there, so what next do we need to do? Someone tell me. Anyone, make a guess. Talked about the good Jesus answer in this class? Say, yeah, take a derivative. Except, before we do that, I make one suggestion. Let's rewrite that ever so slightly. How might I suggest that you rewrite it? 5 can stay 5, minus 4 can stay minus 4, but I don't like taking derivative of something in the denominator. So how could I write that? X to the minus 1. I would rewrite it first, now take the derivative. It's much easier. And what will that be? Get out of there. Okay. Anybody? Four times x to the negative 2. Perfect. Now, if you wanted to rewrite that back in the denominator, you could write it 4 over x squared. Okay? Now, what do we want that to be? That first derivative? What was it saying? F prime of c needs to be 1. So set it equal to 1. Not 0. Rolle's theorem, that's what you would do. This one, set it equal to 1. How do you solve that equation? Not that hard. Multiply both sides by x squared. Okay, and that wipes out the x squared here. You get 4 is equal to x squared, right? Agreed? Now, any solutions for that? Take a square root of both sides. And what does it give you? X is equal to? Okay. Except it's plus or minus 2. Right? Now, you look up here and say, are either of those in that interval? What you said at first is. Positive 2 is, minus 2 is not. Minus 2 is on the other side of 0. Not going to go there, okay? But plus 2 is. So forget about the minus here. Technically, we have to include it, but it's not in the interval, so we ignore it. So x equal 2 should give us that same slope. Well, let's see what would happen if we put a x equal 2 in there. Sure enough, you get, remember this is 4 over x squared, and when you put a positive 2 in there, you get 4 over 2 times 2 is 4, 1. Bingo. Oops. Can't say bingo in Alabama. Okay. So, we did find one value only, for which, now you may have several, this one only has one, okay, for which the slope of the first derivative at some value x equals 2 is the same as the slope between the two endpoints. Good deal. Any questions on that? You see how it works? All right. I'm going to erase this and let's see if they do it any differently. I think not, but maybe so. The slope of the secant line through 1 f of 1 and 4 f of 4 is indeed 4 minus 1 over 4 minus 1, which is 1. Slope of the secant line. That's the line between 2 points. Okay? Then the function satisfies the mean value theorem that it's continuous between 1 and 4, and it's differential between 1 and 4. Would not have been continuous or differential between minus 1 and 4. If that had been the case, throw it out. You cannot do it. Cannot use mean value theorem there. But since this is continuous and differentiable between 1 and 4, you can do it. So you do that. F is continuous on the interval and differentiable on the interval. So take there exists at least one number C in 1 to 4 such that F prime is equal to, F prime of C is equal to 1. Well, solving the equation, F prime is equal to 1. They skipped all the messy parts and went straight to the result, 4 over x squared is equal to 1, which implies that x is equal to either plus or minus 2. However, minus 2 is not in that interval only positive 2 is. So there indeed is the, here is that curve, and as you see, x cannot equal 0. You've got a vertical asymptote here, x equals 0, okay? So that's not happening. That's 4. You can't go across that. But between 1 and 4, on this side, smooth and continuous function. And the slope between 1, 1 and 4, 4 is indeed 1. And the slope at the point. And we didn't figure out what the value was, the point was. Well, all we did was c is equal to 2. To get the second part of that, and they didn't ask for the point. They just asked for the value c. But what you do then, let's go back a slide or two. Well, I guess I erased it all. What we do after we find that c is equal to 2, then we put f of 2 is equal to 5 minus 4 over 2, which is what? 3. 5 minus 2 is 3. So there's your point, 2, 3. Okay? And then you find, so that's the only part we didn't do, they did, but they didn't ask for it. They just said find the value of c. So that's where they got the second part, 2, 3. And at that point, sure enough, the slope is exactly equal to 1. Because the first derivative was minus 4 over x squared, and we already verified when you put 2 in there, you get 1. Okay, slope of 1. Make sense? Mean value theorem. A pretty important and significant theorem in all of calculus. I think you'll see it come up a few other times. Maybe not in this course, but in other courses. A useful alternative form for the mean value theorem, like I said, it will come up, is this. If f is continuous on a to b, differentiable on the open interval a to b, then there exists a number c in a to b such that f of b is equal to f of a plus b minus a times the first derivative. Okay? Which is exactly what we were doing before, because if you subtract f of a from f of b, you get f of b minus f of a here. That disappears there. Divide by b minus a, and you get f of b minus f of a over b minus a equal f prime. It's just another formula. This writes it as a line. This is the slope. Basically is a point slope formula type rendition of it. Exactly the same type thing, only you got 2 points and a slope. Keep in mind that the polynomial functions, rational functions, and trigonometric functions are differentiable at all points in their domains. Okay? You have to pay attention here. They're not differentiable at all points, but they're all points in their domain, which means any place where you have a vertical asymptote, that's excluded from the domain. So anytime we are within the domain, then polynomial functions, which are everywhere, rational functions except for the vertical asymptotes, and trigonometric functions, again, except for your vertical asymptote, they all fit the bill here, because they're all smooth, continuous functions except for the vertical asymptotes, okay? And those are excluded from their domain. All right, any questions on that? All right, whoa, unbelievable. This is the let me go back here. Look at this. Here's the problem. For f as a find all values c on the open interval such that this is true. Well, look at the title of it. Finding a tangent line. You didn't find the tangent line, you just found the c. We could have found the tangent line. Let's do that second part and actually find the tangent line once we know that that value c is equal to 1. Okay. Well, no, c is equal to 2 to get the slope of 1. Okay? So I'm going to do it right here, in fact. Okay? With this information here, what is the tangent line? They didn't ask us to. They had the title, Finding a Tangent Line, but we didn't find the tangent line. What would be the tangent line then? We just discovered the point of tangency is 2, 3. We already determined that f prime of c is equal to 1. So what is a tangent line? Anyone tell me? As in a point slope formula. What would that be? This is a calculus, this is algebra. Yeah, we use it all, right? Okay, how would that go? Anyone remember? Is it Monday morning or something? I don't know. Okay. Okay. Point slope formula? Y minus y1. Is this ringing a bell? Equal to what? M times x minus x1. And we have all the pieces we need to fill in the blanks. What are they? Tell me what to write. Y minus 3. That's the y1, 3. Equal m, which is the slope. Right? Slope of the tangent line. That's just the slope of the tangent line is the slope at that point. Okay? That's just 1. We don't even have to write it. So we don't even have to put parentheses. Okay? So what goes next? X minus 2. Perfect. And then you can add 3 to both sides, and you get y is equal to x plus 1. And sure enough, that is the tangent line that goes through here, and we'll see it on this picture over here, hopefully, if we can ever get to it. There it is. Look at that. Y-intercept of 1, slope of 1, y is equal to x plus 1. There it is. They didn't do it. It wasn't required. It was just the title of the problem. Okay. So, and we could have plugged it in here. That's very similar to what we just did. Okay. All right, and that was the end of the slide set. So let's go back and do example 4. Any questions before we proceed? Finding an instantaneous rate of change. Okay? Now, I have a few issues with this problem, not serious, but just practical. 2 stationary patrol cars equipped with radar are 5 miles apart on a highway. So here's the cop car, that's the little flashing light, and here's a cop car with a little flashing light. And they are 5 miles apart on the highway. Okay? As a truck passes the first patrol car, so here comes the truck here, you know, coming this way. Its speed is clocked at 55 miles an hour. Okay? I'll put V is equal to 55 miles per hour. Okay? 4 minutes later, so timeline, this is now 4 minutes later, he passes the second patrol car, and his speed is clocked at 50 miles per hour. So V2, I'll put this as V1, is equal to 50 miles per hour. Okay? It says, prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. Okay? Now, sure, you can use it using the mean value theorem. Okay? But that takes an awful lot of work. I mean, not a whole lot of work, but it takes some work. But guess what, folks? If he went 5 miles in 4 minutes, guess what he's doing? His average speed is greater than 60 miles an hour, right? Because 5 miles in 5 minutes would be 60 miles an hour, right? A mile a minute, which is 60 miles an hour. So if he did it in 4 minutes, there's no way that he couldn't have exceeded 55 miles an hour in there, because his average speed was greater than greater than 60. So to me, yeah, you could do the problem using mean value theorem, but why? I mean, why mess with it? But here and it's a rather awkward problem to do with mean value theorem, but you can do it. Here you have a slope of 55, and here you have a slope of 50, and you know that in 5 miles in between the two, you have to find the slope there, but he did it. I mean, it's kind of a ridiculous problem, okay? The time when the truck passes the second patrol car is 4/60th. That's 4 minutes later out of 60 minutes, 1/15th of an hour, okay? And it's so awkward to do this. So S of 0 is equal to 0, S of 1/15th is 5. The average has to be 75 miles an hour. But guess what? You could do that without using calculus at all. Just 5 miles divided by, and you could do the same thing that they did there, 4/60 hours, okay? Or you could just do it in minutes. It doesn't matter than convert to hours, and this would be the same as 5 times 60/4. So 60 will go into 4/15, and 5 times 15 is 75 miles an hour. So if they average 75 miles per hour, no way he couldn't have broken the speed limit in between. So there's much easier ways to do that problem than the way they suggested. And that does finish 3.2. Pretty short section, okay? Any questions so far? All right, homework exercises, either 3 or 5, they're both located at calcchat.com. 7 or 9, they're both at calcchat. 9's at calcview. Any of the odds 11 through 23, they're all at calcchat. 13's at calcview. Either 25 or 27, they're both at calcchat. 29's at calcchat. 31 is at calcchat and calcview. 33 or 35, they're both at calcchat. 37's at calcchat. Any of the odds 39 to 47, they're all at calcchat. 47's at calcview. Any of the odds 49, either 49 or 51, they're both at calcchat. 53's at calcchat, and you can look into explore doing 55 or 57. They should both be at calcchat. And then I would say choose any of the odds 59 through either 59 or 61. They should both be at calcchat. You can think about doing 63 if you're interested. Then either 65 or 67 are both at calcchat. 69 or 71 are both at calcchat. Then there's a couple true false, 73 and 75. There should be both at calcchat. Then if you're interested in pursuing, there's a couple of proofs in fact several proofs. Any of the odds 77 through 83 are all proofs. You can do those if you'd like. Some of them pretty easy, some of them might take a little more work, and then 85 is another using of the mean value theorem. Any questions? All right. None? So then let's go on and complete. Three, 2. And we're going to move on to 3, 3. And while that's coming up, let's see, what are we at? 9:30 almost. So we've only been going for about an hour, but I have noticed at least one person has gotten up to go. Do y'all need a break now or whatever? Wait till 10? 10 is about midway through the class. Or would you rather, because this is a decent point of breaking, you need one now or want to go till 10? Till 10? Okay. I guess Malcolm will be back soon, hopefully. So we'll go from current slide. And we're still in Chapter 3, Applications of Differentiation. Now we're going to talk about increasing and decreasing functions and the first derivative test. Okay. Now, I keep being concerned because we've been going an hour. So for more than an hour, I've had my computer on with it plugged in, hopefully charging. I've still got a red light on one battery, and that's not a good sign. So either it's not charging well or the battery is really getting pretty lousy. Usually by this time that light would have gone off, gone blue again, but it hasn't. So anyway, 3.3, increasing and decreasing functions. Objectives here are to determine the intervals on which a function is increasing or decreasing. We're going to find that pretty simple. And we'll apply the first derivative test to find relative extrema of a function. Okay? Now, just a little bit of warning. We're going to do test after test after test. This is the first derivative test, which is okay. It's good. It's a good test. But in no time, we're going to then do another test that basically is going to make this one not quite obsolete, but a little bit, you know, at least pieces of it obsolete. So just stand by for that as we go through different sections here. So let's first talk about increasing and decreasing functions. What does it mean for a function to be increasing? What does that mean to you? Yeah, it's going up. As you go from left to right, the function is going up, increasing. And for it to be decreasing, it's going down as you go left to right. Be sure you keep the x going from left to right, then the function's going up or down. Okay, now, just a little bit of point of thought here. If this function's increasing over a certain interval, and then later is decreasing, what must have happened somewhere in between? All right, let's back up and let me ask it another way. If the function is increasing, what is true about that function everywhere that it's increasing? What does that represent? My best effort to make a slope. What about the slopes? They're always positive. And if it's decreasing, they're always negative. Now, if it's a smooth, continuous function, increasing on this end, decreasing on this end, what must it have been somewhere in the middle? First derivatives are positive here, negative there. What must it have been in between? 0. Or a possibility of not being defined. That could have happened too. So we can't rule that out, but certainly it seems like if it's positive over here, negative over there, it seems like it had to be 0 somewhere in between. So we'll see if that's the case. You'll learn how derivatives can be used to classify relative extrema as either relative minimum or relative maximum. First, it's important to find increasing and decreasing functions. Here's the definition. A function f is increasing on some interval when, for any two numbers, x1 and x2, on the interval such that x1 is to the left of x2, less than x2, that implies that f of x1 is also less than f of x2. Because as you're going from left to right, if it's an increasing function, the function value must be increasing as well. Right? So that would imply that if x1 is less than x2, f of x1 has to be less than f of x2. Whereas if a function is decreasing on an interval, when for any two numbers x1 and x2, again for x1 being less than x2, oh my goodness, he's still my heart. Okay, he's come to that. All right, Ryan is here. All right, good deal. All right. If x1 is less than x2, that implies that f of x1 must be, they've got that backwards, don't they? Sorry about that. That should be a greater than sign. Okay? Shame on them. They got it wrong in the book too, and I marked it in the book as well. I'm going to mark it in red even. Okay? That's greater than f of x2. If it's a decreasing function and x1 is less than x2, then f of x1 has to be greater than f of x2. That's a greater than sign. Wrong here, wrong in the book. Okay, sorry about that. I don't know how we could be in the 11th edition and that mistake happened. Unless they just put it in this time. Okay. The function is increasing when, as x moves to the right. Remember, you always are increasing on x. As x is increasing to the right, the graph is also moving upward. Decreasing when its graph is moving downward as x is going left to right. So here's a function here. It's decreasing on the interval. It appears to be from minus infinity all the way to a, but at a it stops decreasing and now becomes constant. Joy? All right, good deal. Okay. And it's constant on the interval from a to b, neither increasing nor decreasing, but constant on the interval from a to b. And then from b to positive infinity, it seems to be increasing again without bound. Okay? So there is what we mean by increasing and decreasing. And then they threw this in down here. Derivative of f is less than 0 when it's a decreasing function, equal to 0 when it's a constant function, and greater than 0, in other words, positive, when it's a increasing function. So now, whenever you're thinking function increasing, decreasing, or constant, we're thinking in terms of that, think in terms of derivatives. Negative derivative, zero derivative, positive. Okay? Pretty easy concept. Okay? So, as shown in the theorem below here, a positive derivative implies the function is increasing, negative derivative implies that the function is decreasing, zero derivative on its entire interval implies that the function is constant on that interval. Exactly what we saw in the last illustration. This is now the theorem. Let f be a function that is continuous on the closed interval from a to b. Differentiable on the open interval a to b. Okay? If f prime is greater than 0, positive, for all x's in that open interval a to b, then f is increasing on that interval. Now notice I went my hand like this. It doesn't have to be like that. It could have been like this. It's also a decreasing function. It could be increasing like that or increasing like that. Either one. Okay? If f prime is less than 0 for all x's on the interval a to b, then it's decreasing. It could be decreasing like this or decreasing like this. Either way, as long as it's decreasing. If its first derivative is negative, then it's decreasing on that interval. And if f prime is 0 for all x's on that interval, then that's a constant function. One that we saw much earlier. Pretty simple polynomial function. F of x is equal to c, or whatever the value is. Always constant. Any questions on that? Okay, here's example 1. Find the open intervals. Now notice they say open intervals. Whenever they talk about intervals of increasing, decreasing, they don't include the endpoints of those intervals. They leave them open. Open intervals for which f of x equal x cubed minus 3/2 x squared is increasing or decreasing. Now, does that mean we just sit down and start plotting points and plotting points and plotting points and seeing if we can figure out where it's increasing and decreasing? You could, but that's the hard way. And guess what good mathematicians are? A little bit lazy, always trying the easier way to do the problem, okay? So how would you suggest we do it? Change my ink color. Okay. What would you do? What's the Jesus answer? Take a derivative. Okay. F prime of x is equal to what? Of course, you have to take it. What would that equal to? 3x squared. Help me. Minus, what you say? 3x. Okay. All right. Now, if we're trying to find where the open intervals on which the function is either increasing or decreasing, basically what's going to be true about the first derivative on those intervals? Where it's increasing, what's going to be true about the first derivative? Positive. And where it's decreasing? Negative. Okay. Now, just a little time out here for a moment. What kind of function is this? F of x and also f prime of x. What kind of functions are those? Say again? I can't hear what you said. Okay. What kind of functions are they? Remember we mentioned 3 earlier on a slide earlier. It may have been in the last section. Let me see if I can find it. No, it was in the last section. We mentioned 3 types of functions in a slide just a few minutes ago. They were polynomial functions, rational functions, and trig functions. Is this any one of those? It's a polynomial function. Now tell me something that's true about polynomial functions. It's not necessarily true about rational functions and not necessarily true about trig functions. So it's true about some trig functions and some rational functions, but not necessarily true. It's always true about polynomial functions. 2 features. Sounds like jazz too. The first part anyway. Smooth. Polynomial functions are always smooth. Never any cusp or angles or corners or other things, which means they are, if they're smooth, they're also, Jesus answer, differentiable. Okay? Now, the other thing that's true about all polynomial functions, not necessarily true about all rational functions or trig functions, is polynomial functions are always continuous. They're smooth and continuous. They never have any breaks, corners, smooth and continuous. Rational functions can have vertical asymptotes where they're not continuous. Trig functions can have vertical asymptotes where they're not continuous. Polynomial functions never have vertical asymptotes. They're always continuous everywhere. Okay? And they're always smooth everywhere, means they always have derivatives everywhere. So, if that's the case, what we're looking for is where the first derivative is positive and where it's negative. And if it's smooth and continuous, what must it be in between being positive and negative, or negative and positive? What must it be at the turning point? Talked about this in an earlier section. If it's increasing here, decreasing there, first derivative positive here, negative there, what must it have been somewhere in between? 0. Find those critical values where that first derivative either is 0 or doesn't exist. For a polynomial function, it's always going to be where it's equal to 0. So it's going to exist everywhere. So let's first figure out where it's equal to 0. So let's set it equal to 0. Okay? What does that tell you? What can you do? Factor. And how would you factor that? How would you factor that? 3x times, say again, x minus 1. Perfect. And then what do we do with that factored form? What does this tell us? Either x equals 0 or x equal positive 1. Okay? Those are the two places where this function has a 0 slope. X equals 0 and x equals 1, or wherever those happen to be, has a 0 slope. That means everywhere on the left side of 0, that function is either going to be increasing or decreasing. That means somewhere in between x equals 0 and x equals 1, it's either increasing or decreasing. And it also means somewhere on the other side of x equals 1, it's always either increasing or decreasing. Because these are the only two places where it's equal to 0, smooth and continuous. It can only be increasing or decreasing in between those points. So what we need to do is pick a test point. Something to the left of 0. Give me a number less than 0. -1. Sounds like a winner to me. Okay? So let's do f prime of minus 1. Okay? Plug it in, plug it in. Now, you can either plug it in the top version or the second version. I don't really care. Actually, second version is pretty easy. What would that be? Put a -1 for x. Second?
0.
No. Put a -1 in for x. -3 times -2, that's going to be positive 6. Guess what? What's the function doing there? Increasing. Well, if it's increasing there, it's increasing everywhere on that interval. So from minus infinity to 0, this is increasing. Did everybody see that? 0 is a place that stops and changes. Everywhere before that, it had to be positive. You can pick other points and check them too, but I believe you'll find that be the case. Okay? What's the next interval we need to check? Between those two. Give me a point between those two. Say again? Is that 0.5? 1/2? Is that what you said, 1/2? Okay, let's use 1/2, okay? So let's take our first derivative, f prime of 1/2. Okay, what would that be? Okay, it'd be 3/2 here, which is positive. No. Oh, no, it's not. Because here it would be plugged in the second part, that would be -1/2. 1/2 minus 1/2 is -1/2. And what's that? We don't care what the value is. It's negative. Less than 0, right? So therefore, what's it doing there? First derivative is decreasing. So from 0 to 1, it's decreasing. It's a decreasing function because the first derivative is negative. Okay? I said that backwards. So we need to do a test point to the right of 1. Want to pick one?
You mind whether it's the derivative form or not? Like we never use like the standard form.
Okay, say this one more time.
We were plugging in, we never use the standard form. We always use derivative.
You can use either one. You have to plug it in the derivative, either that one or that one. It doesn't matter. It will give you the same answer. Right? Okay. I just use the second one because I don't have to square anything. I find students make more mistakes when they're squaring than when they're just using linear form. But you can do either one. So you need to pick a point somewhere to the right of 1. Pick one. 2. Okay. Let's plug in and see what alpha prime at 2 is. This is what they call the first derivative test. Plug it in, plug it in. What do you get? 6 times 1. Which, who cares what the value is? So what we're interested in is greater than 0. So what does that tell you about the function? Increasing. So from 1 to positive infinity, again, it's increasing. Okay? That's what they find the open intervals on which this function is either increasing or decreasing. Increasing these two intervals, decreasing that interval. Okay? Make sense? All right. You start off with doing the same thing we did before. Find the derivative, set it equal to 0. That gives you the turning points. Now, if that derivative is not defined, it may also be a turning point, so we'll consider that. This gets back to what critical values are. Places at which the function might conceivably be changing in some way or another. Okay, first derivative is 0 or first derivative doesn't exist. So let me erase my scratch here. Anyone need it any longer? Okay. Then let's see how they do it. Note that f is differentiable on the entire real number line, and the derivative of f is x cubed. Oh, derivative of f is, that's not the derivative, that's the original function. F of x is x cubed minus 3x squared. And f prime then would be 3x squared minus 3x. And then it's to determine the critical numbers, set that first derivative equal to 0, which is what we did. We factored it, and you got either x equals 0 or x equal 1. Those are your critical numbers. That tells you a couple of things. It's either where the function could potentially be changing. Doesn't guarantee it's changing, but it's potentially changing. So then we'll use those to set up a few test points. Because there are no points on which f does not exist, you can conclude that x equals 0, x equals 1 are the only critical numbers. Okay? We concluded that. And then the tables summarize. The book likes to do it in tables. If you like tables, go for it. Okay? But notice what they do. They use those critical values, x equals 0 and x equals 1. Okay? They look at something to the left, they take a test value just like we did, and they chose the same one we did, minus 1. They plugged it in and found out it was 6, but the important thing, it was positive, greater than 1, means the function has to be increasing everywhere in this interval from minus infinity up to 0. At 0, we know that the slope is 0, so it's changing something there. May not be changing direction, but it's changing something, changing the slope. Okay, go from positive to 0. Okay, so then we choose another test point in between 0 and 1, and that we chose to be 1/2. Same thing they did. They found that it was negative there. It was negative 3/4. Who cares what the value? That it was negative. That means the function is decreasing between minus 0 and 1. And then chose another test point to the right of 1, x equals 2. Found out it was positive again there, so it's increasing there. So it's increasing, decreasing, increasing, equal. All right. Let's see if they draw the graph. Here it is. Now, things they did, we did not do to draw the graph. Once they found that first derivative equals 0 here, they went back and plugged it in here. When you put a 0 in for x, you get a 0 for y. So you know that's 0, 0. When they got a positive 1, x equals positive 1, also gave you a 0 slope. Plug in a 1 here, you get 1 minus 3 halves is negative 1 half. And sure enough, there it is at 1, negative 1 half. Okay? And then when you plug in values, you could plug in values of this. If you plug it into the first derivative, you'll find it's increasing here, decreasing here, increasing beyond that. Remember over here, positive 6 slope, negative 3/4 slope, positive 6 slope. So it's going up really dramatically here and here. The decrease is not as radical, but it's there. You don't need to grow the graph, but the graph shows you indeed what your first derivative test told you is truly correct. Any questions? See how it works? Okay. That was example 1. That did not flip the page. All right. Example 1 gives you one instance of how to find intervals on which a function is increasing or decreasing. The guidelines below summarize the steps followed in that example. This is basically going over what we just did. Let f be a continuous on some interval a to b. To find the open intervals on which f is either increasing or decreasing, use the following steps. Locate the critical numbers. You tell me what the critical numbers are again. What's the rule for finding critical numbers? What will they be? For the first derivative, it's either zero or doesn't exist. Either where the first derivative is 0 or doesn't exist. Locate the critical numbers of f on that. You do that by taking the first derivative, and where that first derivative either is 0 or doesn't exist, those are your critical numbers. Those set up your test intervals. You may have 1, 2, 3, 7, whatever. Okay? And then, on every test interval, pick a point, not one of those critical numbers, but on one side or another of a critical number, and determine the sign of f prime, the first derivative, at the test interval for each of the intervals. A test value on each of the intervals. Use the theorem to determine whether f is increasing or decreasing on each interval. If that test value is it's not going to have a 0 slope, and it's not going to have an undefined slope, because those are your critical numbers. So it's either going to be positive or negative. Okay? If it's positive, it's increasing on that interval, the entire interval. If it's negative, it's decreasing on that entire interval. Those guidelines are also valid when the interval a to b is replaced by either minus infinity to b, a to positive infinity, or minus infinity to positive infinity. You do the same thing. It doesn't have to be a finite test interval. All right. Time for a break, or you want to go on a little bit longer? A little bit longer, or your break? I'm willing to go now if you want to. Break? Okay, let's take a break. All right. Let me put this on pause. Okay. Good question. Let me re-emphasize that. If it's clarification, absolutely. You know, I don't know what you're asking here, what are you meaning here, but it's a, how do you work this problem? No, I don't want to do that one. However, find any problem in the book, or any book, if you have a different math book, calculus text, and remember, every time I do a homework exercise, I tell you You can go to Calc Chat or Calc View. Find any of those places, write down a problem like it or come up with a problem like it. I'll do anything from the book or your book, any book. So if it's clarification, yes, I do want to do that. Or if it's how do you do this, find something in the text, I'll do anything in the text or any text. Okay, does that answer what you're asking? Okay. What's that?
I think I might have.
Okay.
149, 2.5.
Okay, 149, is that what you said?
Yeah, page 149.
Okay. Let me mark my place here. 149?
Oh, no, that's number 2.
What'd you say?
Number 15?
On 149,
Yes.
number 15. All right. So let's go back to a place. Here we go. All right. This is from page 149. This is 2.5 exercise. Oh, hey, I meant to go to unlock your door for you. I forgot to do it. Sorry. 2.5 exercise number 15, you said? 15. All right. It says finding a derivative. In these exercises, find the derivative by implicit differentiation. That's the one you want, right? So here's the problem. Sine of x plus 2 cosine 2y is equal to 1. Did I copy it right? I think so. Equal 1, I got it. Okay? Now, it says, find the derivative dy dx by implicit differentiation. There's no way you can, well, there may be some way you could isolate this, but it would be really awkward. It would be bad, okay? Much easier to do it by implicit differentiation. So how would that go? Okay, derivative of sine x is what? Cosine x plus, well, I think so. I'm going to leave the sign off for now. Derivative of the second part. All right, it is going to be a minus 2 sine of I'm stuck there. 2 times the sine of what? Two y times what? Chain rule. There's links in a chain, okay? Chain rule. You did the derivative of the outer part, now you do the derivative of the inner part.
You never find a derivative
Of 2y.
Yeah, the outside of 2 is a cosine.
Okay, the outside of 2 was part of that. It's already done.
All right.
It was part of that one. The inside, that's one we want to take the derivative of now. It's what? 2y prime, because y is a function of x. Remember? You don't have to do that with x, because x is a function of x. Dx dx is 1, but dy dx is not necessarily 1. In fact, that's what you're looking for. So that's the chain rule part. Okay? And then you got the equal sign. What's the derivative of 1? 0. Okay. Now what do you do? Okay. Cosine x by itself. So I'm going to move the minus to the other side. So this will be a cosine x is equal to, now notice you got 2 2's here, so that's going to be 4 sine of 2y times, I'm going to write this as dy dx. That's what y prime is, right? That's what you're wanting to isolate. That's what you're looking for, the dy dx. That's why we moved it to the side by itself. So what do you do at this point? Say again? Ooh, we've already done a derivative.
You said division.
Division, absolutely. What do we divide? 4 sine 2y. Both sides. And that wipes out everything here. So your dy dx, or y prime, whatever you want to call it, is equal to 1/4 cosine x over sine 2y. Now, I don't know how they give the answer in the back, and that really doesn't matter. If you were doing web assign, which it isn't set up yet, I'm going to try to get that set up this week, if possible. It depends on how slow they are at Cengage. But that is a perfectly legitimate answer. Let's just check the back of the book and make sure that's what they got. And this is, what is this, 2.5? Is that what they got?
2.5? No,
2.5, number 15. They got cosine x over 4 sine 2y. Yeah. I put the 1/4 out front, but it doesn't matter. Does that answer your question? Whoever had it? Helpful or not? Okay. Any others? Okay. So if you don't happen to have the book, find someone with the book and find one like it. Okay. But again, that's why I go over every time when I'm doing the assignments. These problems are found at CalcChat or CalcView. And if you got a computer, there's no code required. You can go, anyone can go to calcchat.com and find these problems, or calcview.com and find the problems. So that might be helpful. Okay. Any others? Anybody? Okay. All right. So let's get back to where we were, which is first derivative test. Oh, man. Yeah. Okay. Now, this is a slide we took the break on. New terminology here. A function is said to be strictly monotonic. Okay? Now, what does the prefix monos mean? Same. Okay? One, basically. Okay? Mono, one. Monomial is a single-term polynomial. One. A monotonic on an interval when it is either strictly increasing in the entire interval or strictly decreasing on the entire interval. Now, here's a function, f of x equal x cubed. You probably drew this back in an algebra class sometime. That's strictly monotonic because here it's obviously increasing like crazy, but it's slowing down its increase and slowing down until it almost flattens out here. Okay? But then it increases again here. Now you might say, but isn't the derivative 0 there? You'd be absolutely right. It is 0 there. But does that mean it's not increasing up until then? It really is. And it's 0, the derivative right there is 0, but just past it, it's increasing again. So that's strictly increasing. Even though the derivative did pause for one point to become 0, it was positive here, positive there. It just happened at one point to be 0, but it never went negative. So that's strictly increasing. And that's also strictly monotonic. One direction, either increasing or decreasing. On the entire, on this one, entire real number line. Okay? That's what it means to be monotonic. Now, remember back when you were doing, hopefully you were doing, oh, there's something I meant to check. I'm glad I just did think of it. We've got, in this class, 3 people who have never shown, and except for those 3, everybody turned in the first test. So therefore, I'm sorry to break right in the middle of this, but I'm afraid if I don't think about it now, I'll forget about doing it. I think they were all turned in last time, and now I've got to find them. Here they are. Okay. Hold on just a moment. There's that memorandum from the Vice President I was looking for earlier. Okay. All right. Your first test, and as I said, one person has turned in a research paper so far, but all right. Let me turn back these first tests to you. I wish I could have gotten them to you sooner, but didn't have them all. Maya's not here today. Reginald is. Whoa, we lost Reggie. Huh? Oh, I see. Okay. Taylor. Lyle's not here today. Huh?
Do you have the time in class to explain one question at a time?
What's that?
Do you have time in class to?
Oh, yeah. I mean, you can always ask a question. Okay, never any problem doing that. Patrick's not here today. I'm trying to get these in alphabetical order while I'm doing it. Maya's not here. Patrick's not here. No, Reginald's left. I wish I remembered his name. Lyle's not here. Malcolm's here. Jasmine's not here. Terry's not here. Joy is here. Ashley's here. Devin's not here. Here. Miriam's here. And all right, good deal. Sorry I didn't get these to you before the break. I just forgot about getting those returned. I'd have done that sooner. I could have gotten. Okay. And everybody here did get the second test, right? That's not, you did not? Okay. You did not. Okay. I'm sorry. Let me find those two. I just had them on top and I didn't realize. I asked that earlier, but that's before y'all came in, I guess. One. Okay. That's 2. Again, this is printed on one page. You can use front and back But to show all your work, I'm almost certain you've got to use some additional paper. Yeah.
Okay, can you explain the research paper, please?
I'm sorry.
Can you explain the research paper?
What about it?
Can you explain it?
Okay. What do you mean, explain it?
What are you writing about?
You choose your topic. Anything that has anything to do with the context of this course. I've named several people we've hit, theories, applications, anything such as that. You choose your topic. And if you want a full description on Blackboard when you go to the home page of Blackboard, there's a series of tabs on the left-hand column, and they're grouped in 8 to 10 in a group. The first group, there's things about the syllabus and my locator card. That's all that you got there. In the second group, there's something called handout, PPTs, PowerPoints, and more, or something like that. You go to that group and click on that. You'll see, I think the very first thing listed in there is research paper general instructions. Okay, that lists it all. Or go way down in that until you find the YouTube videos. You go to the first video, it says syllabus. Now, it's not the first at the top, because at the top, those are videos from last time I taught the course. But you go down to where this course starts and find the one that says syllabus. Click on that one, and I go over that same research paper instructions in gory detail. So you can find it there, too, on that first YouTube video. I'll answer any specific questions you got, but I just didn't want to go over the whole thing again. Did you have a specific?
No.
Okay. All right. All right. Good deal. Sorry, I wish I'd have thought of that. At least at break time, I would have taken care of that where we weren't recording. Okay. So what do we mean by strictly monotonic? It's either strictly increasing or strictly decreasing, as shown here. Even though it might pause momentarily to become a slope of zero, it's always increasing. If you were to pick values real close to zero here, no matter how close you get on the left-hand side, you'll find they're still slightly negative going up to zero, and then right on the past that, slightly positive, and so they're always increasing. Even though the slope is at 1.0, they are always increasing. Okay? The function shown here is not strictly monotonic because it's increasing to here, but constant from here to here and then increasing there. So there is a place where it's not increasing. A point where the first derivative is zero, that's fine. An interval where the first derivative is zero, not fine. That's not monotonic. Monotonic here, and monotonic here, but not the whole thing, because this is not this. It's increasing here, but not increasing there. Mono means one. It has to be going in the same direction constantly. Any questions? Okay. So let's do the first derivative test. As if we hadn't already done the first derivative test. Here's what we got. After you have determined the intervals on which the function is increasing or decreasing, it is not difficult to locate the relative extrema for the function, of the function. For instance, I figured 318, this one here, which was the one we just did, okay, from example 1, the function f of x is equal to x cubed minus 3 halves x squared has a relative maximum at 0, 0, a relative minimum at 1, negative 1 half. Okay, where do those occur? They occur at the places where it goes from being increasing to decreasing. Has to be a maximum. If it's increasing up to that point, decreasing past the point, that has to be a relative maximum. Not an absolute maximum, but relative maximum. Then if it's decreasing here and then changes here and becomes increasing on the other side, relative minimum. got to be. Decreasing before you got there, increasing after you got there, that is your minimum value. Relative minimum. Local minimum value. Certainly it's not total minimum because over here it's much less. Over here they're greater than that one. So these are not absolute, but they're relative minimum and maximum. Okay? So anytime it changes direction from increasing to decreasing, got to have a relative maximum. Decreasing, increasing, got to be a relative minimum. That's your first derivative test. Similarly, f has a relative minimum point at 1, negative 1/2, because it's decreasing immediately to the left of x equal 1 and increasing immediately to the right of x equal 1. The next theorem makes it more explicit, and here's that theorem. The first derivative test. Let C be a critical number. Hey, what makes the critical numbers again? Y is equal 0. So again, first derivative equals 0, or another possibility. First derivative does not exist. Two possibilities for your critical values, critical numbers, where the first derivative is 0, the first derivative does not exist. Okay, let C be a critical number of the function f that is continuous on an open interval I containing the point C. If f is differentiable, so it has to be differentiable on the entire interval. What does that mean? The first derivative exists everywhere, okay? And that means there's no breaks or abrupt changes in slope, okay? So f has to be differentiable on the interval, except possibly at C, at those critical values. It could have a discontinuous first derivative there, but it can't be discontinuous itself. Then f of C can be classified as follows. If f prime changes from negative to positive at C, relative minimum of C. If f prime changes from positive to negative, relative maximum at C, f of C. If f prime of C is positive on both sides of C, or negative on both sides of C, then C is neither a relative minimum nor a relative maximum. Later we'll give it another name. We'll call it an inflection point. But we're not calling it that yet. But that's will be another terminology coming up later. So if it's the first derivative is negative on the left side of C, positive on the right side, it has to be a relative minimum. If it's positive on the right side of C, positive on the left side of C, and positive on the right side of C, even though it has a critical point there, it doesn't have to have a relative maximum number. Again, we'll call that a different name later. Okay? If it's positive on the left side of C, negative on the right side of C, relative maximum. Negative on the left side of C, but negative on the right side, neither maximum or minimum. Okay? Again, we'll give another name for that later. So here's example 2. Find the relative extrema, that means maximum or minimum, of this function. F of x is equal to 1/2 x minus sine x on the interval 0 to 2 pi. Okay? So, now, especially when it says open interval and they say relative extrema, this doesn't include the endpoints. Absolute maximum or minimum or absolute extrema, and it was a closed interval, then you would. Here we not. This is relative and they're open interval. Okay? What's the first thing you're going to do? Plug in what?
0 to 5.
Second?
0 to 5.
Okay. You're evaluating at the endpoints. I just said we're not evaluating at the endpoints. Okay? If you're looking for absolute maxima, yes, you do it. We're not looking for that. This is open interval, not including the endpoints. So what's the first thing you do here? Take a derivative. So what's f prime of x? Do it for me. My computer is occasionally blinking off, but it seems to be stable now. 1/2 minus cosine x. And what do we do with that derivative? Set it equal to 0. You're not finding increasing or decreasing here. You're finding your critical values here. Okay, and what does that tell you? That cosine x has to equal 1/2, right? You just added cosine x to both sides and switch sides. Okay, now what? You figure out any values on the interval from 0 and 2 pi that give you that cosine x is equal to 1/2. Anyone know of any of those values from 0 to 2 pi where cosine x would be 1/2? So again, pi thirds, you said? That's perfectly correct. So x equal pi thirds. Any others? Okay. If it helps, picture the cosine function from 0 to 2 pi. Okay. It starts at 1, and at pi halves, it goes down to 0. At pi, it's down to -1. And at 3/2 pi, it's 0 again, and it goes back to 1. That's a pretty ugly rendition of it, but that's what it is. 1/2 here, and you already identified that to be pi thirds. One other place where it's 1/2, any ideas on where that is? 5 pi over 6. Is that right? No, that's not right. 5 pi over 3. Okay. I can't hear well. Is that what you said? Absolutely correct. Short of 2 pi by the same 1/3 pi. It's 1/3 pi less than 2 pi. All right. Now, we have our critical values. These are our C's. Okay? Now, what do we have to determine now? So, I'm going to erase this so you don't confuse it. This is just your first derivative function here. That just gave you the values. Okay? I don't want to confuse that and the original function. So I'm going to take this off for now. Okay? Now, what might you choose to do? Those are the places where their first derivative is equal to 0. There are no places where the first derivative does not exist, because both 1/2 x is a polynomial function, sine x is a trig function. Both of those are continuous everywhere. Not all trig functions are, all polynomial functions are, but only sine and cosine are continuous everywhere. Okay. So, second, plug in a what? Test value. Excellent. Choose me a test value. Need something to the left of pi thirds. I wouldn't go past 0. I wouldn't even include 0. How about pi 6? Or even pi fourths will work, right? Both are less than pi thirds. You want either one of those? Which one? Pick one. Pi fourths, okay? Okay, let's plug pi fourths in your f prime. What is cosine of pi fourths? Let's plug it in, this one, not this one down here, that. And forget about the equal 0 here. That was just to find our critical values. But let's plug it into the actual derivative. Pi fourths. What is, yeah, 1/2 minus. Okay, so this would be f prime of pi fourths would be 1/2 minus root 2 over 2. Okay. All we're interested in is whether it's positive or negative. Any guesses? Really? Because root 2 is about 1.414, right? So this would be negative, less than 0. That's all we're interested in. What does this tell you? At x equal pi fourths, this is decreasing. The original function is decreasing. In fact, everywhere from 0 to pi thirds, the function is decreasing. Okay? Because of pi fourths is decreasing. So everywhere between 0 and pi thirds is decreasing. What might we choose next? Another what? Test value? Okay. Pick me a test value between pi thirds and 5 pi thirds. I think of a real nice one. Pi. Why not just pi? Yeah, 3 pi thirds, which is pi, right? Okay. So we'll do f prime at pi. And that would be 1/2 minus, and what is cosine at pi? -1. What is that going to be? That's going to be pi, yeah, it's going to be 1.5, but the important thing is going to be greater than 0. So it's positive. So from pi thirds to 5 pi thirds, this function is increasing. Now, what does that tell us? Do we have a relative extrema at pi thirds? If it's decreasing on the left and increasing on the right, guess what pi thirds is? Anybody?
Oh, is it decreasing?
It's decreasing on the left and increasing on the right. Guess what it is at pi thirds? A what? You may be saying, I can't hear well. Minimum? Is that what you said? Okay, the first derivative is 0, for sure. It was a test point. But I'm asking about the function itself. What is the function? If it's decreasing here, increasing here, what must it be at pi thirds? A minima, a relative minimum. That's what we're looking for, relative extrema. So, at x equal pi thirds, and then what's the y value at x equal pi thirds? Go back and plug it in here. Ooh, that's ugly. This would be 1/2 of pi thirds minus, and what sign of pi thirds? Square root of 3 over 3, is that what you said? Okay. No, over 2. Square root of 3 over 2. Okay, I hope you said that. Okay. Whoa! My pen wasn't erasing. There it goes. Minus square root of 3 over 2. Okay? Okay, so this is pi 6 minus root 3 over 2. Ugly value, okay? But whatever that is, that's a relative minimum, okay? And I'll tell you something right now, that is a negative value. Pi 6 is close to 1/2, and root 3 over 2 is greater than 1/2, so that's a slightly negative value. So sure enough, that seems like it's a relative number. Okay, so at pi thirds, comma, pi 6 minus root 3 over 2, relative minimum. Minimum. Okay. All right. Now, what do we do next? We got this as a minimum, relative minimum. We need to determine that. So what do we need to do? Second? What 0? Okay. The first derivative of at that point is 0. That's how we chose the point. But what we're interested in is what's going on beyond that point. So we get use a y'all like them, I just gave you one back. Test point, okay? Test point. I need one between 5/3 pi and 2 pi. Pick me something in between there. Another way to think of this, you could think of this as 10 pi 6 and 12 pi 6. Maybe 11 pi 6. That sounds like a good one, doesn't it? Okay. 11 pi 6. That'll be our test value. We're going to plug that in here. F prime of 11 pi 6. That's ugly, but it's there. Is, I'll do the first part, 1/2 minus, and what is cosine of 11 pi 6? Root 2 over 2, absolutely. No, root 3 over 2, okay. And guess what that is? That's a negative value, isn't it? Because root 3 is greater than 1, less than 2. So that has a bigger negative quantity, so this is less than 0. Okay? In other words, the first derivative is negative. Okay? So that says it's decreasing between 5 pi thirds and 2 pi, you're decreasing. Well, what does that mean? Between pi thirds and 5 pi thirds, you're increasing, and between 5 pi thirds and 2 pi, you're decreasing. What does that mean 5 pi thirds is? Increasing up to it, decreasing after it. What does that mean it is? A maximum, a relative maximum. So 5 pi thirds. Now, do we need to plug that in? I guess we should. That would be 1/2 of 5 pi thirds would be 5 pi over 6. That's the x coordinate. And no, I mean that's the first value here. I'm sorry, I was looking at this. You're plugging in that. Minus what sine of 5/3 pi? Negative root 3 over 2. Okay? Now, this time will take a little more work. It's 5, 6 pi plus or minus root 3 over 2. Okay. Now, this value here, 5 times pi, that's going to be something close to 60 divided by 30 divided by 3 is something close to 5, a little bit more than 5. And this is something that's less than 1, okay? So square root of 4 is it. So this is obviously a positive value. So this is, and we already determined that's going to be a maximum. So the y coordinate is 5 pi 6 minus root 3 over 2. That's the y value. This is a relative max. Okay, because it was increasing before that, decreasing after that. So that's where it is. Now, they don't always do it in ordered pairs like this. In fact, I think they probably don't do it in this case. This is example 2, right? I didn't even turn my page yet. They don't list the y value, which is sort of wise of them, up to and including that. Okay. So, all right, for me to erase, that just was a little extra work to do those. I probably shouldn't have. But usually it's better to list them as ordered pairs. Okay, note that f is continuous on the interval 0 to 2 pi. Why? Because polynomials are continuous. Sine is continuous, so therefore the combination of those will be continuous. On the interval from 0 to 2 pi, and derivative is that, just what we found. When we set that equal to 0, we find that cosine x is 1/2, which gives our critical numbers of being pi thirds and 5/3 pi. Okay? Oh, wow. My screen died. Okay. I don't know what it's doing. It's just jumping all over the place. Okay. So pi thirds or 5/3 pi are your critical numbers. Okay, because there's no points on which f prime doesn't exist, you can conclude that these are the only critical numbers, so therefore they're the potential relative extrema. Okay? All we know is potential. So we set up our table. We set up pi thirds here and 5/3 pi here. Pi thirds here, 5/3 pi here. Okay? We pick a value somewhere between 0 and pi thirds. They use pi fourths just like somebody suggested here. We found out it's negative, so it's decreasing before you get to pi thirds. Okay? But after pi thirds, between 5 pi thirds and 5 pi thirds, they chose pi in between there, which is exactly what we chose. That is positive then, so you're increasing after that, so this must be a relative minimum. Increasing after this, and then when you get to 5/3 pi, pick another. They use 7/4 pi. We used 11/12 pi or something like that. 7/4 pi will work as well, and we found out it's negative there, just like ours is negative. So it's decreasing after there, so that made that a relative maximum. 5/3 pi a relative maximum. And by applying first derivative test, you conclude that alpha is a relative minimum at the point x equal pi thirds. They didn't figure the y coordinate of that. Smart for them. And a relative maximum at the point where x was 5/3 pi. And they didn't figure the y value there either. We did, and this is relative minimum here, relative maximum there. Notice I put open circles here because our original problem said that was an open interval from 0 to 2 pi. So it doesn't include either one of those. Neither one would have been a max in this case, but we don't even have to consider it because it was an open interval. Relative minimum here, relative maximum there. Make sense? deal. All right. Now, they list that as the last slide, which is not the last example. We have example 3 and 4 to go, at least, and 5. Okay, so let's go back and do... What's that? I'm sorry? Oh, okay, okay. So, yeah. So all of you got your test back. Let me get a copy of it. Okay. It seemed to be the most often, frequently missed one. So this will be test 1. Problem 4. Is that what you asked about? Test 1, problem 4. Okay, let f of x equal piecewise defined function 3 minus x anytime x is not equal to 1, and it's 0 when x is equal to 1. Okay? Determine the limit as x approaches 1 of f of x. Okay? Now, what does the limit mean? It's what the function tends to be doing. Say again? I can't hear you. Yeah, it approaches, but it doesn't necessarily equal that. Okay? So if you're getting closer and closer to x equal 1 from the left-hand side, from the downhill side, this will be 3 minus something very close to 1. In fact, probably is helpful to draw a graph. You don't have to, but I think in this case it would be pretty helpful. Okay? Now, if I rearrange this and write it as minus x plus 3, that's the same function, right? Okay? What can you tell me about that function? Okay, so there's y-intercept of 3 and a slope of -1. So it would go down to here, down to there, down to there. Okay, now mine's not very good. Except at x equal -1, it doesn't equal that. It equals 0. Okay, so in other words, this is a function that is like this here and that there. Straight line, slope of -1, y-intercept of 3, but it has a hole in the line right there. So let me, because I put a dot there I didn't need to, take that away. Its value is down there. Okay? Now, as x approaches 1 from the left-hand side, what's the limit? I don't know if you can read my writing. That should be at 2, right? If you approach from the right-hand side, what's the limit? 2. That's the limit. Its value is 0, but its limit is 2 from both left and right. If they had different values going left and right, then no limit exists, even though there's value, but it wouldn't exist. This one, the limit is 2 coming this way, 2 coming that way, so the limit is 2. Does that make sense? Okay. Plugging it in only works if it's a continuous function. This one's not continuous, so don't plug it in this case. Okay? See what the function is doing from the left-hand side and right-hand side. If it's the same thing, the limit exists. If it was different things, the limit doesn't exist no matter what its value is. But if it's the same thing, that's the limit, not the value. Okay? That's what limits tell you. They don't have to be equal to that value. It's just what it's approaching. That okay? Understood? Okay. Any others? All right. Let me erase that. Okay. And we're going to use the same space here. Let me put this back where it was. Okay. This back where it was. And now we're going to do example 3. Find the relative extrema of this one. F of x is equal to x squared minus 4 to the 2/3 power. Okay. Don't have to do this, but it's a good idea. Is this, let's see, relative extrema? That's all they're looking for. Okay. Now, what kind of function is this? Okay. It's what they call a radical function. It's not a polynomial function, not a rational function, not a trig function. It's a radical function. It's got a radical. The cube root. Okay. But a cube root function, tell me at least 1 or 2 things about the cube root function. It's continuous. Because you can take the cube root of negative numbers or positive numbers. If that was a square root, okay? You have to only have positive numbers in there. Cube roots, you can do any number. So it is a continuous function, and it has derivatives everywhere. Okay? So it's also a smooth function. Okay? So guess what we do next? Take a derivative. Very good. So f prime of x is equal to 2/3 x squared minus 4 to the negative 1/3 power times 2x. Good deal. Remember the chain rule, okay? So let's write that a little differently. 2 times 2 is 4x over 3 times, and I'm actually going to write this back as a cube root. Even though they didn't write it this way, I think it may be easier to evaluate. The cube root of x squared minus 4. Does everybody agree that's the same thing we have here? This 2 and that 2 are both in the numerators as well as the x, so that's 2 times 2 is 4. You have a 3 in the denominator, and this thing to the minus 1/3 would be 1 over, and 1/3 power would be the cube root of that. Agreed? Okay. Now, why did we take the first derivative? Because you said to. Now, why? What's the first derivative tell us?
Slope.
Okay, and what slope are we most interested in? What do we usually do after we've taken the first derivative? Yes, exactly. And what are the critical points? Tell me the 2 criteria that we look for critical points. Where the what? Slope is equal to 0, or where the slope or does not exist. Exactly. Undefined or does not exist. Okay, can anyone tell me where that slope will be 0?
0.
When x equals 0, that numerator is 0, so at x equals 0, the f prime equals 0. So that's a critical point, x equals 0. Any others? No other places where the first derivative is 0, you're absolutely right. But how about where the first derivative doesn't exist? What are at least 3 things that would make a derivative not exist? If the denominator is 0, is one really big one. Anything make that denominator 0? Well, obviously 3 can't be 0, so that's out. 3 is 3, it's not 0. But can this part ever be 0? We have. Or? Yes! So there are 2 more places where that. Now, if you had a negative number under a square root or a fourth root or any even root, that also makes it not exist. But this is a cube root. That's fine. You can have negative numbers in there, but you can't have 0 because it's in your denominator. Okay? So the other 2 places at x equal minus 2 or plus 2 f prime dne does not exist. Okay? So there you have your other. So we have 3 critical points here. Okay? What might we choose to do? Yes, do some test values. Give me one. Let's call this x sub 1. Give me a first test value. Where might we choose it to be?
Would you do -2 below? Like,
Okay. Say that one more time.
We would do -2 our function below.
You need something to the left of -2. -2, you know, it doesn't exist there. Okay? So you choose something to the left of -2, like -3. So x1, just to have something to call it, or maybe t1 equal -3. So let's do f prime of -3. And that would be 2/3 of, no. Let me go back and use that form. Okay. That would be 4 times -3 over 3 times the cube root of 9 minus 4. Right? Now, all I'm interested in is the sign, the SIGN sign of this thing. Anyone want to hazard a guess what the sign of that is? I'm sorry? The SIGN sign. It's going to be a negative because this is negative, that's positive, this is positive. No question here. The denominator is positive, the numerator is negative, so this is going to be less than 0. Okay? So that tells me that from anything to the left of -2, which goes as far as negative infinity, to -2, what is this function doing? Decreasing. Okay? Now, need something else? T2, another test point. Give me one. Well, -1, how about that? Between -2 and 0, right? So -1, so let's do that one. F prime of -1 will be 4 times the -1 divided by 3 times the cube root of -1 squared is 1 minus 4 minus 3. Okay? Now, I'm not really interested in the value of it. I want to know the sign, the SIGN sign of that. It will be positive because the numerator is negative, but the denominator is also negative because the cube root of a negative number is negative, and that's positive, so it'll be negative. So this will be greater than 0. So that tells you between negative 2 and 0, the function is increasing. Okay, so what does that tell you about negative 2? At x equal negative 2, what is that? Decreasing to the left, increasing to the right, stand up, sit down, fight, fight, fight. No, that's a different thing. Okay? Is a minimum. Negative 2 is a minimum. Okay. We actually ought to say a relative minimum, but it's okay. It's a minimum value. Okay? Next. Need another test point. I wouldn't go that far. We've only gotten to 0. Second? 1. Let's do T3 equal 1. You could go on over there, but just don't get yourself confused. So at T equal 1, F prime of 1 is equal to 4 times 1 over 3 times the cube root of, and 1 squared is 1, minus 4 is minus 3. What does that tell you? This is negative, less than 0. So if it's okay, what does that tell you about the interval? From 0 to 2, you are decreasing. So if it's increasing to the left of 0, decreasing to the right of 0, what does that tell you it is at 0? What is that? Maximum. Increasing to the left, decreasing to the right, relative maximum. Okay? I don't have enough room to write my next one, so I'm going up top and write it. Okay? What's my fourth test point? Pretty exciting stuff, isn't it? Yeah, no problem. Pick me a fourth test point. You could do 4. Let's be easier and do 3. Okay? It may not be any easier, but 4 will probably work quite well too. 4 would definitely work well. So there, F prime of, let's go on and put 4. It won't be any problem doing that. Be 4 times 4 over 3 times the cube root of, what's 4 squared? Second? 16 minus 4 is 12. That's the cube root. What can you tell me about that? I don't care what the value is. It's positive by a big shot, okay? 4 times 4 is 16, that's positive. 3 times root 12, cube root of 12, that's positive. So this is positive. So what does that tell you about the interval? From 2 to positive infinity, what's it doing? Increasing. Okay? And if it's decreasing to the left of 2, but increasing to the right of 2, what's it doing at 2? At x equal 2. What is that? What is it again? I can't hear. You may have said it right, I just can't hear. Decreasing to the left of it, increasing to the right of it, what is it at 2? Minimum, right. Relative minimum. Make sense? All right, let's see how the book did. Okay? I think they did their derivatives correctly. Good for them. They left it in that. Well, where is their final answer? Okay. You can conclude F as a relative minimum at negative to 0. They actually calculated it now. a relative maximum at, they left it as the cube root of 16, so that's at x equals 0. A relative minimum at 2, and that would be at 2, 0 again. We didn't calculate it, but we could have. See, that's what drives me crazy about it. Sometimes they calculate the point, and sometimes it doesn't. Here they did. Okay. Make sense? That was example 2. All right. Example 3. Any questions? Think we have time for example 4. Now, here's something, folks. At example 4, those of you who don't have books can actually go to the absolutely free website, larsoncalculus.com, and see example 4, interactive version of this type of an example. So you can actually go through it and do it yourself with help from the interactive version. Find the relative extrema of f of x is equal to x fourth plus 1 over x squared. What would you do with that problem? I'm sorry? Okay, what do you mean by that? Make it as x to the minus 2? Okay. That's an okay thing to do. Sometime I would do a little bit differently here. Notice this. Isn't that the same as x fourth over x squared plus 1 over x squared? Agreed or not? Okay, what's x fourth over x squared? X squared. And then now I would write the second part as plus x to the minus 2. Then I'd write it as that. Just makes things maybe a little easier. Maybe not, I don't know, maybe you don't like it this way, but to me that's the easiest way to do this. And again, what you need to be a good mathematician? A little bit lazy. Find the easiest way. This is going to be, I think, the easiest way. So what's the next step we take? Anybody? Help me, somebody. Take a derivative. Our prime of x would then be what? 2x minus 2 times x to the negative 3. Perfect. Now I'm going to do another timeout here, okay? I need to gather the team around and talk about something here. As soon as you see it, actually in this form, you could have written something down which would have been a pretty good thing to write down. Guess what x can't equal? 0. Okay? So x cannot equal 0. Not in your first derivative, though that's true there too, but x cannot equal 0 anywhere in the problem. Okay? This is a discontinuous function. This has a vertical asymptote, x equals 0.
Why you say that?
Because you can't ever divide by 0.
Oh, okay.
And notice what, if you try to put a 0 in here and a 0 up here, you get 0 plus 1. You get 1 over 0. That's not an indeterminate case. That's a does not exist case. That x cannot equal 0. You have a huge discontinuity there. Okay? So x can't be 0. Period. Period. All right. Now let's look at your first derivative. What do we consider about it? Why did we take it in the first place? Critical numbers. And what are the critical numbers? What 2 conditions do you consider?
Can be 0, can be
or undefined. Exactly. Okay, so first we're going to consider where this is equal to 0. Well, I want to rewrite this to do that, so I'm going to rewrite it as 2x minus 2 over x cubed, set that equal to 0. It seems like I'm going in circles here, and I kind of am, because to solve this, I like it back in regular notation, not in exponential. Okay? Okay. So what I need to do here is multiply everything on both sides by that denominator, x cubed. So I'm going to multiply this by x cubed, this by x cubed, and this by x cubed. And what does this give me? 2x to the fourth minus 2, because those go away, is equal to what? 0. Okay? And then I can factor out a 2. 2 times x to the fourth minus 1 equals 0. And I can divide out the 2. And that still equals to 0. But what can I do with that x to the fourth minus 1?
Oh, you can add 1.
I could do that. You could also do right? Equals 0. And you can take this one yet another step. You can't take this one anywhere else. X squared plus 1 times x plus 1 times x minus 1, and that's equal to 0. Okay? And what does that give us? X equal 1 or minus 1. Those are our only two critical values. Oh, wait, only two places where the first derivative is 0. Is there any place where that first derivative doesn't exist? At 0, but guess what? The whole function doesn't exist at 0. So that is not a legitimate critical number. Now, I don't know if the book counts it or not, but the function doesn't exist there, so it has to be a number what the function exists to be counted as a critical number, and the function doesn't exist. So we're down to these two, okay? So guess what we're going to do with those two? Second? Okay. Test value, okay? And what would be the first test value you choose? I really don't care what order you do them, but give me a test value. How we doing on time? Okay. Negative 2 sounds like a good one. Okay, let's do your first derivative at negative 2. So f prime at negative 2, and let's use this form here. 2 times negative 2 minus 2 over negative 2 cubed, right? And again, all we're interested in is the sign of this. We don't really care what the value is. 2 times negative 2 is negative 4. Now, negative 2 cubed is negative 8. And the negative times negative would be a plus, and 1 over 8 would be 1 over 4. 2 over 8 would be 1 over 4. Now, I'm not interested in the value, but what's the sign of this? This is negative, less than 0, which means that between negative infinity and 1, negative 1, what's the function? If the first derivative is negative, decreasing, okay? Now I need another test point. Not a very good choice. Why? Doesn't exist there. Okay. But you do need something between negative 1 and 0, so negative 1/2 or negative 0.5. So let's do this one. T2 will be at negative 1/2. Okay, so F prime at negative 1/2 will be, and we'll go back to this form kind of here. That would be 2 times a negative 1/2 minus 2 over a negative 1/2 cubed. All right. 2 times negative 1/2 is going to be anybody help me there? 2 times negative 1/2. Negative 1. And then we got a minus times another minus, because negative 1/2 cubed is going to be negative 1/8. And that would be a positive then 2 over 1/8. Right? Which would be 2 times 8 over 1. Which would be 16. So minus 1 plus 16 is going to be positive by a long shot. So this is greater than 0. So what's the function doing between negative 1 and 0? Increasing like crazy. Okay? So what does that make negative 1? Anybody? Huh? Okay. Decreasing from the left, increasing to the right, minimum, relative minimum. So at x equal minus 1, relative minimum. Okay, now, that always comes out looking like a M. Okay. This time, are we going to calculate the value there? Oh, that's not too bad. If we plug in minus 1 for F, that'd be minus 1 to the 4th power is 1. 1 plus 1 is 2. Divided by minus 1 squared is 1. So that's going to be 2. So that's going to be at x, at the point minus 1, 1. Isn't that what I just said? No, I said 2, didn't I? Minus 1, 2. Okay. Yeah. Minus 1, 2, relative minimum. Okay? Let's continue. Another test point. Between 0 and 1, what might you choose? 1/2. So F prime at 1/2 will then be 2 times 1/2 minus 2 over 1/2 cubed. I think you can tell me, okay, 2 times 1/2 is 1, and when you cube this, you get 2 over 1/8, which would be 2 times 8 over 1, so that's going to be a minus 16. So that's going to be a very negative number, less than 0. So what can you tell me there? Between 0 and 1, it's decreasing. Now, don't go back and try to tell me that at 0, this must be a maximum. No, at 0, it doesn't exist. There is no point at x equals 0. But we need to know this so we can evaluate our next point. The only two critical numbers were at 1 and minus 1. We've already determined what it was at minus 1. We need this to determine what it is at 1. So we do need a fourth test. Don't go back here and tell me at 0 it's a maximum. Increase to the left, decrease to the right. At 1 it's not, at 0 it's not defined. So that's why you need to do that right up the top. X cannot equal 0, so don't try to make it a maximum. What's happening there is it has a discontinuity there, but in both cases it's going to positive infinity. So there is no value there. So our fourth test point would be, did you say 2? Yeah, why not? Okay, so f prime of 2 is going to be 2 times 2, I can probably do that one, minus 2 over, what's that, 2 squared? Or 2 cubed? 2 cubed. Okay? So that would be 4 minus 2 over 8, which is minus 1/4. I don't care what value it is, but what is the sign? What is the sign up? Positive. That's greater than 0. So between 1 and positive infinity, it is always increasing. And if it's increasing, if it's decreasing to the left and increasing to the right, what does that make it at? 1? Decreasing from the left from 0 to 1, increasing from 1 to infinity, relative minimum. So this one has 2 relative minimum. And we can actually calculate it there. X equal 1 and y is equal, you put in a 1 in here, 1 to the 4th is 1 plus 2, 1 is 2, 2 over 1 is 2. So again, a relative minimum there. Okay? Now, without graphing it, but I'll let you see them graph it. Thank goodness they did. Here it is. It is not defined to x equals 0, but you still have to do a test point between the two places where it has the first derivative is 0 and that derivative doesn't exist, even though this doesn't produce a maximum min for you because the function's not defined there. Relative min on that side and on that side. That's what the function looks like. Oh my goodness, okay. All right. And I think we're out of time, aren't we? Okay, so we got example 4 done. We still got to do example 5. That's going to come next time. Okay? And for those who did get here late, let me remind you of this. Not a big deal. My office hours tomorrow normally would have been 10:45 until 4:30. I've got a doctor's appointment in the morning at 9 o'clock, so I'm not even going to come to campus until after the doctor's appointment. And then I'm going to make up my 8:30 class at 11, so I'll be in class from 11 till 1:15. And then, so my office hours will be 1:15 till 4:30 tomorrow. I'm sorry? And I didn't give you homework exercises here. Let me do those quickly. 3 at Calc Chat. Any of the odds 5 through 9, Calc Chat. 5's at Calc View. 11 through 17, all at Calc Chat. 13's at Calc View. 19 to 39 at Calc Chat. 21's at Calc View. 41 to 47 at Calc Chat. 41's at Calc View. And I'll stop there. We'll pick up the rest of those later.
I just want to let you know that I'm not going to be here Wednesday.
Wednesday, okay. Mm-hmm. All right, good. Thank you for telling me. Okay. Okay, are you saying something to me or just talking? Okay.
And Mr.
Yes.
Tell me, what's the criteria on that paper that we're writing? Like the criteria.
Okay, what do you mean by that?
Like, is it just on how this discovery affected math or its usefulness?
Anything such as that would be perfectly fine. You can write about a person, a theory, an activity, an application, a YouTube video that explains this better than I do or the book does. Anything like that. Pick your topic, anything to do with Calculus 1 and how you can apply it or whatever.
In the STEM program, are you possibly a part of it in any way?
Yeah, I'm part of it, but it's mostly done on the Birmingham campus, so I'm sort of remote from it. But it's a good program. I mean,
do you know of any way I could I'm gonna apply, but I'm gonna apply in the fall. Is there You know any people I necessarily need to talk to or the proper way of handling it? Like any tips for people applying?
Okay.
Like any tips as far as applying in the fall for the STEM program? Like maybe I should talk to.
Okay. Well, two people on this campus that probably have a pretty good knowledge of it would be Dr. Thomas. You know who she is?
No.
She's on this.
Oh yeah, yeah. She's over Honor Society, right?
She's what?
Is she over Honor Society? Because she has an
Yeah,
office down here.
exactly. And also Mr. Holloway downstairs, who is also Honor Society. Both of them. Mr. Holloway's director. She's co-director. Okay. So they know a lot about the STEM program as well because they work together a lot with that. Over on the Birmingham campus is Dr. Briggs.
Yeah.
And but if that's what you're asking about, then you might want to check with one of them. Some of the biology instructors on this, see, all the biology instructors are mostly over there, but when they teach over here, they're over here. So Dr. Ellison is over here Tuesday and Thursday, and Dr. Lapatna is over here Tuesday and Thursday. I don't think she is as involved with it as maybe Dr. Ellison. Dr. Wilson probably would know even more, but she's mostly on the Birmingham campus. And I think that's all our full-time biology instructors now. Those would be the best bet. On this campus, Dr. Thomas and Mr. Holloway. They'll probably be good. Okay. And they may recruit through for honors college too, I don't know. But because you literally.
That's how that works a lot
Yeah.
of times.
No, I mean, no. If they see you're a good prospect, they may like you to be consider that as well. All righty.